Hello, my name is Francisco Meza, and in this presentation, I am going to talk about an imperfection measuring rig I developed here at the University of Sheffield while doing my PhD under the supervision of Jurgen Becque. We have been using this measuring rig to record geometric out-of-plane imperfections of cold-form steel sections, and we have developed a very simple and inexpensive calibration technique which allowed us to achieve imperfection measurements of unprecedented accuracy. It is well known that the buckling response of cold-form steel members can be significantly affected by geometric out-of-plane imperfections, for example by reducing the local carrying capacity or stiffness of the member, or even triggering particular buckling modes. Geometric out-of-plane imperfections are often categorized according to their similarity to the buckling modes. So we can refer to them as global imperfections, which are often in the shape of the global flexural buckling mode, or cross-sectional imperfections, which might follow the shape of the local or distortional buckling mode. So in order to record this type of out-of-plane imperfections, we built the measuring rig, which is shown in this figure. The measuring rig is able to record out-of-plane imperfections over a length of 3 meters, and it consists of a traverse system with 2 electric motors which are used to move a laser displacement sensor along high precision bars in 2 orthogonal directions. The traverse system has 6 adjustable supports which are bolted to the rigid frame, which is shown here in blue. And the rigid frame also has 6 adjustable supports which ensure that the entire rig is fully resting on the floor. The specimens to be measured are placed on 2 adjustable beams which span across the rigid frame, and both the height and the position along the frame can be adjusted. The laser displacement sensor is able to measure its distance to the target surface with a reported accuracy of plus minus 0.0075 millimeters. The measuring range of the laser sensor is between 65 and 95 millimeters. Therefore, a crack handle is used to ensure that the laser sensor is at the appropriate distance from the surface to be measured. In order to record the out-of-plane imperfections of a specimen, first we need to place the specimen on the adjustable beam supports with the surface we want to measure facing the laser sensor. In the figure, the surface we are measuring is the web of a channel. And then we move the laser sensor along different lines on the target surface. In this case, we took measurements along 3 lines: the corners and the middle line of the web. The out-of-plane imperfections of any point in the web can then be obtained by interpolation, as shown in the figure. We have used this technique in the past to measure the out-of-plane imperfections of single sections and build-up sections, and here in these figures you can see some examples of the type of geometries which have measured. Using this type of setup, the accuracy of the out-of-plane imperfection measurements is largely dependent on the strictness of the high precision bars along which the laser sensor is moved. Nowadays, it is possible to obtain traverse systems with high precision bars, which can guarantee very small out-of-strictness tolerances. However, the smaller the tolerances, the higher the cost of the system. As an example, the traverse system we used here had a reported out-of-strictness of 0.4 millimeters over a length of 3 meters, which is pretty good and perhaps suitable for measuring the global flexural imperfections of a channel about the minor axis. However, it might not be enough for measuring the global imperfection about the major axis, which are known to be of smaller magnitude. This level of tolerances is also not suitable for measuring imperfections associated with local buckling, which are known to be of less than 1 millimeter in magnitude. Another important issue is that the real tolerance that the measuring system can achieve is highly dependent on how well the system has been installed. Also, if for any reason the frame is moved or inadvertently hit, this might affect the strictness of the guiding bars and therefore the measurements. For this reason, in order to obtain reliable imperfection measurements, it is very important to be able to measure the out-of-strictness of the guiding bars so that it can be removed from the measurements. In this study, we measured the out-of-strictness of the guiding bars by generating a virtually flat surface, and then measured the out-of-strictness of the guiding bars relative to that surface. So in order to generate the flat surface, we took the advantage of the fact that a liquid at rest tends to form a flat surface. The liquid we chose to generate the flat surface was milk because its surface is reflected to the laser sensor and its viscosity is sufficiently low to obtain a measuring surface which is virtually perfectly flat. So we used a shallow container and we fill it with milk. The container was designed to be wide enough to ensure all the measurements taken on the milk surface were sufficiently far away from the edges of the container to avoid introducing errors due to surface tension effects at the boundaries between the milk and the container. Readings on the milk surface were taken exactly along the same longitudinal lines as the imperfection measurements on the channel webs. This permitted to correct the out-of-strictness of the longitudinal as well as the transverse guiding bars. Here you can see the imperfections of the guiding bars we obtained by measuring the milk surface. As the manufacturer specified, the maximum deviation from strictness of the guiding bars was around 0.4 millimeters over a length of 3 meters. In order to assess the accuracy of the measuring rig, we measured the web of 3 plane channel sections in 4 different positions. The nominal dimensions of the channels used in this study are shown in this table. You can see that 2 of the channels had a length of 3 meters and the third one had a length of 2.5 meters. When carrying out the measurement of the out-of-plane imperfections, the channels were placed on the adjustable beam supports, with the beam support placed at a distance of 5/9 of the length of the channel, as you can see in the figure. This was to minimize the deflection of the channel due to its self-weight. Imperfections were recorded along 4 longitudinal lines, and readings were taken every 1 millimeter. After the measurements were taken, the imperfections were adjusted so that the imperfection amplitude at the 4 corners of the surface was 0. Here we can see the 4 different positions of the channel relative to the measuring rig, in which the out-of-plane imperfections of the channel web were recorded. So assuming that the thickness of the channel web is constant over the entire web, by comparing the imperfections recorded with the channel in position 1 and 3 or 2 and 4, the errors introduced in the measurements due to the flexural deformation of the channel can be determined. The figure on the right-hand side shows the imperfections recorded on the web of one of the channels after the out-of-strictness of the guiding bars was corrected. The horizontal axis in the figure has been normalized, but it corresponds to a length of 3 meters. If for each measured line, we plot the imperfection difference calculated using the expression shown in this slide, we can clearly see the effect of the self-weight on the measurements taken. The imperfection difference closely follows the expected flexural deformation due to the self-weight of the channel multiplied by 2, which is represented in the figure by the red dashed line. Here we can see the imperfection difference after removing this deformation of the channel due to its self-weight. For reference, here I'm also showing the imperfection difference obtained for the other 2 channels included in the study after the out-of-strictness of the guiding bars and the deformation due to the self-weight of the channel were removed. The accuracy of the imperfection measuring rig and the associated measuring procedure was estimated using the imperfections recorded along each line on each of the 3 channels web, and with the channels in position 1, 2, 3, and 4. According to the central limit theorem, if the source of error in the measurements is random, the measurement error should be normally distributed around the actual value. The error associated with the measurement at a location x along the channel is given by equation 2, where mu sub I is the actual value of the imperfection. However, since the actual value of the imperfection is not known, this was estimated using the imperfection readings with the channel in positions 1, 2, 3, and 4, using equation 3. If the actual value of the imperfection is estimated using equation 3, an error estimate, which in this case is given by the symbol Cassi, can be obtained using equation 4. Here I'm showing you the distribution of the Cassi values obtained using equation 4, combined for all measuring lines, channel positions, and channel specimens. In the figure on the left, the error was calculated after accounted for the out-of-strictness of the guiding bars and the self-weight deformation of the channels. And as we can see, the distribution of the error approximately follows a normal distribution, which confirms the random nature of the error. The figure on the right-hand side shows the distribution of the error before accounting for the out-of-strictness of the guiding bars and the self-weight of the channels. In this case, the distribution of the error is no longer normally distributed, revealing the bias in the error introduced by the out-of-strictness of the guiding bars and the self-weight of the channels. This table shows the cumulative distribution of the estimated error. So if we adopt the 95% confidence interval to define the accuracy of the measuring procedure, we obtain that the accuracy of the measurements after accounting for the out-of-strictness of the guiding bars and the self-weight of the channels is plus minus 0.04 millimeters. However, if the out-of-strictness of the guiding bars is not corrected, the accuracy of the measurements is around plus minus 0.4 millimeters, which roughly corresponds with the maximum deviation from strictness observed from in the guiding bars. So to conclude, in this presentation I have shown you the development of an imperfection measuring rig which is able to record imperfections over a length of 3 meters. The accuracy of the readings were found to be limited primarily by the out-of-strictness of the guiding bars and the self-weight deformations of the specimen. A novel calibration technique was used to correct for the out-of-strictness of the guiding bars. The calibration technique is inexpensive and easy to apply and made it possible to achieve imperfection measurements with an estimated accuracy of plus minus 0.04 millimeters over the full 3 meter length of the rig. Thank you for your attention.